part 3 of the unit on soil formation or its origin will consider the organization of soils. We have seen how soils form over time from different types of rocks, as these are broken down into smaller components and chemically modified. In spite of the great diversity in starting material, topography, and climatic history, soils as they develop and mature tend to differentiate into well-defined horizontal layers. The resulting organization is called a soil profile, and it is the vertical display of soil horizons. Now, observations of many geological formations, such as canyons, cliffs, and ravines, reveals the presence of distinct horizontal layers or strata composed of different rocks. These multiple strata may each be many meters thick. Now, if one looks closely at the soil that accumulates on the surface of the topmost stratum, one will see that a similar organization of layers exists. The different layers can be seen when deep holes or cuts are made in the ground. Here one can see the dark upper layer on top of a lighter colored layer. Now, the different layers of soil created over time are called horizons. These horizons are used to classify soils by type. A soil horizon is a specific layer of the soil which measures parallel to the soil surface and possesses physical characteristics which differ from the layers above and beneath. Soil horizons differ in a number of easily seen soil properties such as color, texture, structure, and thickness. Other properties are less visible. Properties such as chemical and mineral content, consistence, and reaction require special laboratory tests. All these properties then are used to define the types of soil horizons. Now, the horizons are typically labeled by capital letters. Most soils have three major horizons: the surface horizon A, the subsoil B, and the substratum C. Underneath these layers is the parent rock. And let's look in more detail at some of these horizons and a few other types as well. In many soils, there is an O horizon, sometimes labeled A sub O, which is the topmost layer and is made up mainly of composting organic materials. It is usually less than 2.5 centimeters or an inch thick. Typically, the fresh organic litter is found at the surface, but as the organic matter breaks down, it becomes humus that enriches the soil with nutrients and aids with soil structure and water retention as it mixes with the layers below. The O horizon is found in many soils, but not all. Sometimes this horizon can be buried. Now, the A horizon is the topsoil. This is the beginning of true mineral soil. It is heavily weathered and often granular and porous. It contains humus derived from the O horizon above, which is stable organic colloid. We'll discuss this later in another unit, and gives this horizon a dark color. The A horizon is the most biologically rich layer. Most roots are found in this zone. It can be up to 75 centimeters or 30 inches thick. In the soils of prairies, this horizon can be several feet thick. The B horizon, immediately below the topsoil, is typically 75 to 100 centimeters, or about 30 to 40 inches deep. It contains less organic material than A, but is still heavily weathered. It can have a large amount of clay and accumulates by downward movement, and generally is less porous than A. The C horizon, or substratum, lies beneath the B horizon. It is somewhat weathered and typically has no clay or organic material. It represents the soil parent material. An essentially parent rock then lies beneath the C horizon. There are many more detailed subdivisions of soil profiles that need not concern us here, but it is important to realize that not every soil has all horizons. One or more may be missing. This may be a consequence of recent soil manipulation, such as construction. The absence of soil horizons is typical of constructed landscapes where human activity has been intense. But as mentioned, a distinguishing feature of the O horizon and the topsoil or A horizon is the presence of organic matter that accumulates over time. The organisms that live and die in the soil are considered biological factors or active agents in soil formation, and they contribute to the deposition of organic material in the forming soil. This biological weathering is dependent on the availability of water. Different organisms have different effects on soil formation. For example, animals and microorganisms make soils and form burrows and pores. Lichens and moss that grow on essentially bare rock create a more humid environment where chemical weathering can occur. The attachment of these organisms to the rock surface enhances physical and chemical breakdown of the surface layer. Now, plant roots exert physical pressure and can open channels in the soil where water can infiltrate and accumulate. Different types of roots have different effects on soil. Trees create a shallow organic layer above the soil surface. The types of trees that grow in an area influence the soil. For example, coniferous forests produce acidic leaf litter, and the resulting soil is known as an incepti-soil. In mixed deciduous forest ecosystems such as this one in the Blue Ridge Mountains, organic material accumulates at the soil surface in the O horizon. But nutrients tend to be rapidly removed from the soil, creating a leached layer that is expressed by a lightening of the soil color, usually in the upper part, and labeled A sub E as shown here. Soils from such forests are known as alphisols and have a clay-enriched subsoil. In grassland ecosystems, the roots of grass plants, being rather fibrous and near the soil surface, decompose easily, contributing organic material below ground where turnover is slower because conditions are drier. Taproots may open pathways through dense layers. Grassland soils tend to be deeper and more fertile than forest soils. Grassland plants make the A horizon organic and nutrient-rich. Such soils are known as mollisols, whose parent material is typically limestone-less or wind-blown sand. The differences in soil caused by the plants that dominate a given ecosystem is demonstrated by the different profiles in either forest, prairie, or the transition zone. As climate determines the kind of vegetation that can grow in an area, it in turn has important effects on soil formation. So, we have seen then that natural soils are formed by the combined effects of climate, rainfall, temperature, wind, and organisms, plants, animals, microbes, on parent material, rock, or material derived from rock, over time. Though soil formation is a continuous process, the accumulated components of soil are subject to loss through erosion, the movement of soil particles due to wind, water, and gravity, leaching, the draining away of chemical or minerals, as well as chemical and biological activity or modification. Soil formation is also affected by the many human activities involving soil, even beyond activities associated with growing plants. Now, this concludes the unit on soil formation, but let's consider a few questions for review as you assess your understanding of soil formation. Consider, for example, what is the central function of soil in terrestrial ecosystems? What are the factors in soil formation? What is the role of parent material in soil formation? Why does much of the soil around Columbus, Ohio have a pH greater than 7? What are less soils? What characteristic did glaciers give much of the soil in Ohio? And which horizon in a soil profile is the most abundant in nutrients? Think about these questions as you go over the material that has been presented in this unit on soil formation.